we're off C2.
Right here. 14. 14. 14. All right. Let me make sure we're on business. Guys, you really have to try very hard to remind me to record, because then people who can't be here can benefit from this. And if we go too fast, you can benefit from this, right? So,
are you recording?
Yes?
Remember to record.
It's
That's a Lego. That's a Lego.
all right, and then, okay, so an ice cube is put at a temperature of 20 degrees in a plastic bowl and placed in a microwave oven. The oven is then turned on. When the oven is turned off, the bowl contains water at a temperature of 60 degrees Celsius. Assuming the microwave transfer energy to the ice at a constant rate throughout. Draw a graph below the temperature of the HO as a function of time. This is awesome. All right, sketch it really quick. Don't worry about too much what the number should be. Just to sketch the shape of what should have happened. All right. This is the negative 20 where the ice starts and it ends over there. What happens in between? Right?
Are we supposed to be writing down every
Huh?
H2.
Remember, it delivers heat to it at a constant rate.
Are we supposed to be writing down every question?
You don't need to write down the questions. You need to write the answers, and you write the numbers of the questions. Yes, so you can follow.
Because sometimes you go on too fast and I don't have time to write.
I know. I'm trying to be better. I'm sorry.
No, I'm just saying that.
No, she's right. She's right. Next, I brought buzzards for brain games, and I forgot them at home. I brought buzzards for game games. And starting next class, you can just grab the buzzards and have one in each desk. When I'm going too fast, you just buzz. No, seriously, I bought it for that too. Is that cool?
Well, if we do it for conceptual, I'll be. I love it. I love it when buzzers are involved.
Mister, are you gonna bring your girlfriend to Scandinavia?
Of course.
Isn't she a
Wait.
It'd be such a good trip.
It depends. It might be a
Guys,
different girlfriend at the time.
stop with the rumors of my departure. I love my leaks. All right, let's go. It's actually not a lie. It's the best. I love every day getting in the car and coming here. I enjoy it very much so.
He just doesn't like him in the nostalgia.
I don't dislike. I love Roby. I have no problem with him. All right. So, okay. So, anybody wants to volunteer to write this down on the board? Let's do it. Double Legos this time. Oh, come on, Leon. Let's do it. Hurry up. We got one more to do. I want to ask somebody else to explain what Leon does afterwards. So let's see what he got. No pen. Get another one. Give me that one. Let me throw it out. Yeah, but did you mean that to be a flat line?
Yeah.
At what temperature should that happen, though?
Oh, okay.
Let's fix that. There you go. Okay, there you go.
Oh, okay.
It's difficult to know exactly when or how exactly the line would meet the zero, but we know that when it hits the zero, it's got to go through that latent heat period, right? And the entire thing has to get to zero or past that what do you call that? It's a latent heat, or the heat of fusion in this case, right? You guys remember that. Also remember that, how do we know the lines is straight? Right? Just because the heat is delivered at a straight rate doesn't mean the temperature change is going to be straight. Remember that it's like this, right? So if we are delivering heat at a constant rate, and this is a constant, and that's a constant, well, then this is the thing that's varying, right? How are they related to each other? There's no powers, right? So if this is at a constant rate, then that has to be a constant rate. Does that make sense? Also, you should have seen those graphs in the chapters, right? So it should have been an easy one. Now, we do have to explain why it's like that. It's because of the latent heat, right? That it has to go through. All right. Good? For today, if you want, by the way, there's a Lego box over here. Felipe, can you handle this side over there? Make sure Liam gets 3 Legos, please. All right. Suppose that we have a sample, A, which has 150 grams of ice at -10. Sample B has 150 grams of ice at 0. Same mass, right? Same microwave. Until both samples achieve 30 degrees Celsius, right? Will the time taken to heat sample A be longer than, shorter than, or equal to the time to heat sample B? Go ahead. That's an easy one. Let's get through these easy ones fast.
It makes sense that like
Right, because you start.
Yeah, start at lower temperature so it takes longer.
Assuming the microwave delivers the heat at a constant rate, you need to do more. You need more heat, right, to do the second job. Correct? The first job. Sorry. You need more heat to do the first job of heating A, right? You're like, oh, why can't all you have for Q's be this easy? It has a valid point. By the way, give the mail on Lego. If you guys participate, demand your Lego, okay, to the Lego givers.
Demand.
All right. It does make sense. Now, this is the easy ones. It builds up from this to harder things, right? So that's why we have to go through this to build up to it. Okay. So mixing water and ice. So it's the same amount at the same temperature. All right, with me? You know water can be at 0, right? And still be water. You even talked about distilled water needing condensation nuclei to actually form a crystal, right?
Don't know the power of the dark side.
And we also put in the same amount of hot water at the same temperature in both cases. Now, will the mixture on the cylinder A final temperature be greater than, equal than, or will it be different? I love this question. Very good. See, that's not as easy as you think. Make sure you explain. Drop your pencil when you're ready. So we're pouring, there's the same heat, both substances have the same heat to give, right? The question is, will the final temperature be the same for both of them? Same mass at the same temperature. It reminds us of the problems we did last class where they had these same temperatures, but there's a new twist here, which is the state. Yes?
B would be at a higher temperature.
Why?
Because just like how you said, the latent heat.
Exactly. We gotta go through a state change first, right? And that's gonna take some heat. Meaning there's less heat left to do what? To heat this up. Are you with me? A lot of heat is gonna go to just what? Melt that. You're gonna melt that first before you can start heating it up. Okay? All right. Thermal expansion. Switching gears. Different topic now. All right. A surveyor. So we did a lot of the whole heat transfer questions basically. But all those heat transfer questions was governed by this equation, right? So now we have to switch equations. What equation governs problems like this? It would be the L prime, or area prime, or volume prime, right? Always equals the original length, the original area, the original volume, times a constant, right? Now, I forget what the constant is called. Or is it? It's alpha, alpha 2, or alpha 3. They represent the rate at which this thing, each material has a specific one, right?
No, it's 3 alpha. 3 alpha, like they're multiplying. Yeah, and then 3 alpha is equal to beta.
This is beta?
2 alpha, that's 2 alpha. That's 6 alpha. And then 3 alpha is equal to beta.
Okay.
But it's just,
Okay. All right. Either way, they give you the alpha steel here, right? Is it sure it's not like alpha cubed? Is it just really 3 alpha?
Yeah.
Okay, just making sure. All right. So they give you the linear coefficient of expansion of the tape, and they say there's 100 meters of steel tape, and calibrated to be precisely 0.1 millimeters at a temperature of 50 degrees. So you know what that tape measurement that we use? Is it reliable? Now that you've learned thermodynamics? So we do it on a hot day outside, and we do it on a cold day outside. Now, the actual amount of thermal expansion may be...
It's time for changing temperature.
Oh yeah, of course. Sorry. All right.
I'm here with you.
No problem. Thank you so much.
Who are you?
The brother.
Oh,
Nah, it's friend
friend.
Actually, the friend. Yes.
I'm like, the brothers look kind of alike. Like, you don't look like him.
Is it kind of cool that our school has a fireman on it? I kind of like it.
I think that.
Huh?
No, that's the friend. And then
Yeah, they split the class, the 3 of them. So.
What do they teach?
health.
Then the EMT.
Well, it's not just EMT. The third level of health is EMT, but the first two is just like regular, you know. And the idea is to work them towards being like EMT certified, and eventually someday. Although that actually takes community college classes and stuff like that, but it's pretty cool though.
Because we never even had a nurse. They're like our.
Right, they became our nurses. Yeah. But they're cool. All right, so it's interesting. Let's look at this problem. You don't realize, even if you're talking about, let's say, a 2% variation in length, doesn't seem much. But if you're talking about 2% over 20 meters, right? Now you're like 20 centimeters off. That's a lot. And then you are like the error that you get could be something because of that. You come back the next day, you do the other part of the lab. Now it's a different temperature. There could be, you see? So laser measures don't have that problem, right? It's pretty cool. All right. So this is, by the way, that's another thing that matters. Anybody knows what defines a meter, or used to define a meter?
Oh, it was.
Yes.
I saw the videos too.
Okay.
Was,
You did?
Yeah. It's the amount of distance. No,
Well, not that's now.
no, it
That's
was
now.
They actually had like a block.
Well, that's a kilogram. The meter was literally a stick that was kept in a certain temperature in Switzerland in a fridge, and that was the meter, right? Now it's actually based on the distance that the speed of light will travel in a certain amount of time in vacuum, because that's not going to change no matter what, right? And they also can do it based on the sizes of a standard gold atom, the size of the electron cloud, right? Because you need to have a standard that what? That won't change, right? Because thermodynamics says that it will. So that's the problem. Kilograms is a problem too, because since volume changes and density changes and the G changes, how do you measure a kilogram? Where? At what place of the Earth? That matters. How much mass is a kilogram? So are you with me? Because the scale you use is going to be based on the G of the place. So that's the kilogram also has to now be measured based on the number of moles of carbon-12 atoms. You know what I'm saying, that you have. So right. So they have a distance. The two statements measured at 4-degree day, and the linear coefficient thing. So is the actual correct distance now shorter, longer, or the same? This should be easy. Jilly, what do you think? We're on a hotter day, Jilly. So they measure the distance, right? Yeah, they measure on a day that was hotter, so it's supposed to be shorter. Yes, you're right. All right, good. Give Jillian's point. Very good. What happened? Why is it, Jillian? Why is it supposed to be shorter? Because the tape has what? Whoa, splendid. Expanded. Yeah. Right, exactly. Good. Tippers. These are important. Let's do this. There are two samples of pure substances which are heated at a constant rate, and their temperature as a function of time is recorded. Both substances started as solids, and as you can see, both melted. How can we tell they melted, Felipe? By looking at the graph. If they didn't tell you that they melted, right? Is there anything that from the graph that tells me that a state change took place, Felipe? So you gotta read this chapter if you haven't read it. Attention. But because the thing, okay, everybody's raising their hands. Yes, Miguel.
The reason we know that the substances melted is because at first the temperature is going up, but then it flattens out.
What's
showing that there's a latent heat period.
Exactly. Very good. Very good. He was so professional in speech. Very nice. Give the man 5 Legos. All right. Okay. Now, and he did a good job. He said, okay, now, is the melting point of substance rate? Oh, God, this is so easy. Jesus. All right. Yes. Who has the biggest melting point? A. However, explain your reasoning.
Because it's higher, is above 0 and then the other one.
Okay, very good. Now, is the specific heat of substance A in the solid state greater than, less than, equal than the specific heat of substance B? Now remember, the rate at which things heat up is governed by this equation. Right? If we're talking about two substances with the same mass and they're receiving the heat at the same constant rate, right? the rate at which they change should be constant as well, and you can see that. Both of them have constant rates of exchange, right? But why is one graph more steep than the other if they have the same mass, the same heat, right? It has to be the specific heat. So the heat is the slope, specific heat is the slope then, right? Well, actually, the real thing, think about it, we have temperature divided by time, right? So it's not really slope, but either way, the specific heat is what's causing the difference in the slope. So which one has a bigger specific heat? Now remember what it means. It's how much the specific heat has time in it. Remember that? It's how much energy it takes to create, in a way, not time in it, sorry. It has, because this has time, they're saying it's being delivered at a constant rate. They're talking about power, right? The specific heat is how much energy it takes per unit of gram to make the gram go up by 1 degree, right? So it will take more time to make something heat up if it has a high specific heat. So does that look like a steep slope or a not so steep slope?
It has a high one.
Think about water. Will it have a steep slope, heat up very fast?
No.
No. So the high specific heat means what? Lower slope. So who has the high specific heat here? No, B has high specific heat.
I know, but it changes though. Why does it change?
No, B changes slower. As a solid, we're talking here, guys.
So
As a solid, right? The heat changes slower. Then here, as a liquid, who has the biggest specific heat? Substance A. And we can tell that from the slope, right?
Also, it changes in one state to the
Apparently.
Oh, so you didn't know that?
No, it does. I knew that.
Oh, okay.
Now, this is actually cool. What about the heat of fusion? Hey, did you guys get that, or should we?
Substance A is greater than.
The heat, the specific heat of substance A as a solid is smaller than B. B has a bigger specific heat. How do we know that? It's taking longer for it to heat up. Are you with me? Why is it taking longer for it to heat up? Because it takes more heat to do it, and the heat is being delivered at a constant rate. Right? Now, here's an interesting question. Which one takes longer to actually melt? A takes longer to melt. So who has the biggest heat of fusion? Which is the heat it takes for something to melt or solidify. All right, you know what the heat of fusion is? Is the heat that has to be released when something fuses, right? Or, by the same token, the heat that must be absorbed in order for something to melt, right? So, and with the heat of vaporization, it's called the heat that gets absorbed to make something evaporate, right? Or the heat that has to be released for the thing to become a liquid, right? Now, the heat of fusion, how can you tell? Oh, actually, first of all, let's keep using. Guillermo, what do you think? Who has the biggest heat of fusion here? A or B? 50-50 shot. B. Why do you think B has a bigger heat of fusion?
That's not 50-50.
Why? I was just making him think if we just picked one because it's 50-50. Alright. Where is the heat of fusion in the graph? The flat thing, right? Now, so, as it's changing state, that it does that line. And then, why is it staying so long at that temperature? Because all the heat there is not going for this. It's going to make the substance what? Change the state, right? Now, the heat is being delivered at a constant rate, and yet the temperature of this thing is taking that long to change. Meanwhile, this one takes this long to change state. Which one is taking longer to change state? Why is A taking longer if both are receiving the heat at the same rate? Because A takes more heat to change state, which means it has a bigger heat of fusion. Does that make sense?
What's it called? Heat of fusion?
Heat of fusion is to make it melt or to, I just said it. The heat it takes for something to melt is heat of fusion, which happens to be the same heat that would have been released if it solidified. Yes, Pedro.
But it's the latent heat, and then the following line after that, is that in gas state?
Yeah, that's liquid state. Right. Because they told us it started as a solid. Right? By the way, how do I know something went to gas from all the way to solid? I would have to have what? Two lines. But what about sublimation? So there's such a thing called heat of sublimation too. It is possible to go straight to solid, but they would have to tell you that this is a heat of sublimation thing that's happening. You know, they would have to tell you that. There is such a thing for that. And of course, it takes more energy, of course, right, for that to happen. All right, let me ask you another question. Which substance receives more heat at the end? They are supposed to. It's a trick question. All right, it's equal.
Wait, what was the third one? The third question?
I asked it, the latent heat.
Oh, okay.
Okay. All right. Heat a beaker filled with glycerin. Okay. So the glass beaker is partially filled with a certain volume of glycerin, and the beaker and the glycerin are then heated to 40 degrees. The thermal linear coefficient of expansion, alpha, is this, and the thermal volume coefficient, beta, is that. So see, this is the thing. When you get that and multiply by 3, you don't get that. So I'm thinking, I don't know if that makes any sense. That's what I was trying to explain. See, I don't know. But anyways, it's supposed to be 15, right?
Wait, Lima, that's glass and that's the other.
Oh, fine, that makes sense. All right. All right. So what they're actually, this is actually what the problem's about. So they give you the alpha of the glass, and then they give you the beta of the glycerin, and they're asking you, as the beaker and its constants are heated, will the glycerin's volume level? Because remember, it's at 500, right? So you find the beaker to the 500 ml. Oh, this will be a cool lab to do. All right, that would be a cool lab to do. So you do 500 mLs of glycerin. We could do it on, well, oil or something, but the answer for me is obvious for most things. For glycerin, maybe it's not. But anyways, I do have some glycerin. Now, what you could do is this. So as you heat both of them, which one, the question is which one expands faster. Now, this is an incredibly important engineering thing. Let's think about it. If you're building a road, there'll be steel things, or building a building, and there'll be concrete things. What happens if the thermal expansion coefficients are not matched closely enough? One will go faster than the other, and then you have a structural problem, right? So that a bridge in a road. So if you look at the roads, actually in bridge, next time you look at the roads and you're driving through a bridge, just listen, and you'll hear dum 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 dum. You know what that is? It's a tiny little gap in the road. Why is that gap there? Because if it heats up, you can actually expand a little bit of the concrete because the metal doesn't expand at the same rate. Are you following what I'm trying to say?
Wouldn't metal expand at a greater rate?
It depends. I don't know enough about material engineering to know that, but they actually think I know that's why the gaps are there. I also know that in the sidewalks, that's why the gaps are there. Because in the sidewalk, if you don't have the gaps, when the sidewalk expands, it cracks. So the gaps are in the sidewalk literally to save money to have to redo the sidewalks all the time. And you know roads? Ever wonder, I mean, yes, they have the things to make the water collection on the side, but you didn't have to make that out of concrete. You could just literally put it out of the same material. But why don't they? Why don't they just fill the entire road? It's not because it's less material. It's because you got to leave room for the road to expand. See, it's crazy, but that's actually happening. This building, it is now becoming shorter than it was in the summer because every day is a little cooler, right? And it's actually ridiculous. Houses made of wood up north can lose an entire square foot or more, if more than that. Like you can lose a meter in linearly on the side. The house literally shrinks, and you hear it at night because it goes, it crackles. You know?
Oh, and penis is shrinking.
And penis is shrinking the pool. Exactly, but that's different. All right, so that's why the hot tub thing. No, I mean, I'm just kidding.
Okay.
Listen, there's a line there somewhere about the girl being hot and thermal expansion. I'm just saying. There's a line there somewhere. You gotta think about it. Let's solve the new glass. Hey, if this is the alpha, the beta form would be 15, right? 15 10 to the 6, which is much less, right, than 5.1 10 to the 4, which means by the thing, who is expanding more?
Why is it less? It's more. Because it's -6 and -6.
Right, so this is negative. So this number is a negative number. So that means this one is a bigger number, which means it will expand by a bigger fraction of the glass will expand, meaning it will run out of room, meaning the level will go up. Right? Pretty cool. All right, now let's finally get to the good stuff. PV equals nRT stuff. Please play with the fat. It's excellent.
Lima, you never answered my question.
I have a life.
Okay,
Okay.
I have a life too.
That was like 8:30 at night. I didn't have time for
No,
that.
it was 7:50.
Okay. Oh, I'm sorry. I was supposed to be working at that time. All right. You're good?
No.
He's gonna go.
Did you say what?
Nah, it's
What did you say?
that happens
I don't know. Is that going broke?
Why didn't it happen on October 20th?
Oh, look, oh, fuck. That's double pain. I'm pretty sure what was the answer? That happened to me last
He took the shoe off and it looks big, so he's gonna have to go like check that out.
Oh, it's swollen?
Oh, it's big. Unless his foot is just like that. I don't know.
He said, yeah.
Lego.
Yes. Okay.
Oh, we get Legos for that?
We actually did this. I think we did this problem in the ranking test in the first day.
Yeah.
No, I think we did this problem. Yeah, we did. Because look, we're changing the end.
It was 6 instead of. It was
We didn't have those boxes. Like, I don't know.
And I know, but it's a ranking task one. Look, they're asking about what is it asking about? The pressure. The pressure. They're asking about P. So you solve the equation for P.
They're asking for temperature.
Alrighty. Yes. T. Okay. So, alright. In which case, if they're asking for temperature, we solve for T, and we put T equals PV over NR, right? Okay.
Isn't that uppercase N, which is number of molecules? So it's another formula.
Sure. Alright. PRT. You're right.
Do I help with the break?
They have a golf cart. So just load on the golf cart and that's it. Alright. So, so the pressure is the same for all? No. Guys, if you are given a ranking problem like this and you ask to see, all you have to do is pick one as your base and then give a score for that one. And then all the other ones you give a score as well. So for example, if this is my base, how does B compare to A? Let's do it. That doubles the N. What does that do to it, to the temperature? And it decreases. So let's think about that. Does that make sense? You double the number of molecules. Why would the temperature decrease? Assuming pressure stays the same. That's important. If I have the same pressure but double the molecules, because see, I would think that if you add molecules, you're going to add pressure. You asked that question in the thing, kind of.
Because the volume isn't stated specifically. Like, it doesn't.
But it's a chamber. The gas takes the volume of the chamber. Are you with me? So the volume will never, but it will never change. Are you with me?
Yeah, that's what I'm trying to change.
Oh, you can't change volume on that. Oh, you can. You can press on it. On the top, you can push on it.
I'll figure it out.
Yes. By the way, you can't change the volume. You can change all the variables, including the name of the molecule, everything. FET is very good. Choose to play with that. Seriously, it's really good. Now, the PV nRT. So, what I need an explanation here because I'm asking the question. Okay, why is it that adding molecules does not? Well, it would increase the pressure because you have more things in the same space, all hitting the surfaces, right? But if the pressure stays the same between the two things, right, and the volume stays the same, but you added molecules, what does that mean about the kinetic energy and how it's going to be distributed there? Yes? Yeah, sure.
When they say that
Uh-huh.
the energy has to be spread also to those molecules. So like how you said,
So, right. And what is temperature?
based on the average.
Kinetic energy, which means
There would be less.
there'll be less. So is this? It is. I just want to make sure you conceptually understand why it goes down, the temperature, even though you're adding molecules. Because I think, oh, I'm going to add molecules. They're going to all be moving around. That means it's going to make it hotter.
Yeah, but they move it like.
But if it does make it hotter, if you mess with the pressure too. But it's hard to add molecules and not add pressure. in normal circumstances. Think about it. You blow air into a balloon, you're adding both pressure and molecules. Are you with me? But a fat has a solution for that. You can add pressure without adding molecules. It's really nice. Anyways, let's score it then. Compared to that one, this will be a half. Half of A is what I would call it. Whatever A is, the temperature, there'll be half of A. What about that one? Caitlin, what do you think about the next one? So, what am I doing? Am I changing anything? What's my independent variable this time? The pressure. And so it's going to be, now I'm lowering in the pressure. It'll be half again, isn't it? It'll be half again. Why? What about the third one? I lowered the pressure and the volume. Right? So I lowered the pressure by a factor of half. So I would half it, but the volume was also half. So it'll be 1/4. So this is how you do these ranking tasks. Right? And this will be A. I did.
A is 2.
Yeah, no, I did that. I have both this and this, which are both on the top. So I'm doing 1/4. We talked about that. Alright, so that means it'll be A first, and then B tied to C, and then D. You see that? Let's do one more. We already practiced this in another class. If they have more of this, we'll just do one more. Alright, yeah, rank the pressure. This time we solve for pressure. Please drop your pencils when you're ready so I know. So this is just Boyle's law, pretty much. Pressure and volume. Right? That's Boyle's law, right? I think. Because everything else is held constant. I think. Same number of molecules, because it says it's the same gas. And R is the same for both of them. Temperature is the same for both of them. It's just Boyle's law. Do you guys understand that when those things are held constant, everything here becomes a constant? So you can think of it as a 1 over V, right? Or a K over V. So the only thing that matters is the volume. So whatever you do to the volume does what to the pressure? It's the inverse, right? So if you increase one, the other one decreases.
Or do the forces come into play?
You're also changing the.
What equation is going to be? It can't be that simple. The forces have to do something.
Of course, there's pressure that's being added to it. This is also a thing about that gauge pressure thing, right? Remember the gauge pressure is the atmospheric pressure plus the pressure of the gas?
Isn't it minus?
Or minus, whatever. No, it is. You have to look at both things together. But all of them have 10 Newton disc. No, they changed the disc and the weight that's sitting on it, right? It doesn't change the area.
So it's the same thing. I guess.
It's not the same thing. This guy has 12 newtons of force.
Right. I mean, yeah.
So the atmospheric pressure there is different from the atmospheric pressure. No, it's actually the same as here,
It's 12.
right? This one has 20 atmospheric pressure, and this one has 4 atmospheric pressure. And then you can talk about what the volume is doing to create another type of pressure, so to speak, differentiation between. What's the gauge pressure formula again?
Okay, total pressure equals pressure of no, I do plus.
Yeah, plus. So then that should be like minus the atmospheric pressure.
No. T total is over them together.
Yes, which means, no, that's what he's saying. So he's saying that this would be atmospheric pressure minus the P total.
Wait, so it's rho?
So you're asking, you really want to know that, right? and they're changing things that change this and that, right?
You can't change it.
It's not that bad. Remember what I did last time? We choose A as a base and then go through it, right? So let's do it together. A is a base. Let's quantify a value of B compared to A. Let's think about atmosphere pressure first, or the pressure that's put on it, right? The same. So this number is going to be the same. Yes, Therese.
Can you just do P equals F over A? No? Yeah? No?
Unless you have the area.
Like the area doesn't change.
Oh yeah, the area
Exactly,
is
so it's
equal.
just like
It's just how much, so like
so it's just
A and B will
F.
be the same.
It'd just be the F.
Yeah, you could just use force instead of looking at the volume.
Yeah, you can just look at the force as being done by, yeah, sure. So this will be, that means these two will be tied. This one will be the first, the biggest pressure. And this one will be, right. Huh? Well, so the way you can think of this is that if there was enough pressure down here to push this up, it would have pushed it up. Are you with me? It's not pushing it up, it's an equilibrium. That's what Jillian's saying, right, Jillian? It's like if saying the force of the gas pushing it, whatever pressure it has to be equal to the force that's being pushed on it. So you can think about all that stuff, but ultimately, it's just about the force that's being pushed down on it. So 20 tied last, right? That's simple.
Wait, are you sure A and B are tied?
Yeah, because it's trying to confuse you and making using Boyle's law like I first said, but it's really not, because it's basically Newton's third law. The force is going down must be match the force that's pushing it up, you know. Otherwise, they'll be moving. Okay.
Would it be the same
It's the same
volume?
thing.
Ooh. Okay.
Wait, can I ask you a quick question?
Mhm.
When you're looking for the number of molecules in a thing, you use ideal gas, but what units would you apply for each one? For pressures, ATM or Pascal?
Pascal.
Pascal.
I think so. Pascal is a unit of SI unit, no?
Yeah.
So
But and for temperature Celsius or Kelvin?
Kelvin.
Kelvin. Because I tried it with both on the quiz, on the test, on the practice test. I wouldn't get the same.
Guys, answer the question. Please come with lab plans for next time. Calorimetry stuff, the fat stuff, a bunch of different things are in the activities folder. Come with a plan, otherwise you get less points. And Naya, are you still here with us? Let's have the mentality of actually writing very complicated lab reports. Because you do this stuff and then you turn in 3 things and I can't.
It was the last day, so I just had.
I know, I'm just saying. Try to help you out, brother. Alright, so, what am I doing here? Oh, yes. Ideal gas. Very good question. Yes, give him 2. So it's Pascal's the standard SI unit. Meters is the standard SI unit for volume, right? Or liters. Or liters. So you can just look at the constant. The constant is in joules, Kelvin, and moles. So which means it's got to be in Kelvin. All right?
But when I was doing the questions, I would do them in Kelvin, and I wouldn't get any of the answer choices. And it was like simple. You know, PV is equal to, then you divide it by R over T. R is 8.31. And it happened to me a couple of times.
Oh, that's what it is. The mass is also in grams.
Sorry, one math.
kilograms. Oh my. All right. Does anyone have an answer here to share with us? All right. Anybody? All right. Are you actually thinking about it or talking about something else? Come on, Robert. No, they say each gas occupies half a cylinder. So, yes. You were? Oh, sorry. Absolute temperature is twice as much on the right than it is to the left. It's solved for this. Volume is the same for both. You're doubling on the left side one number, right? But then the temperature is half. So the pressure is the same. That is true.
What if it's not
That's true. But what we don't know, hey, is that the problem there is that it doesn't tell you anything about what it's about to do. So it could just be right now. Because if you let go like this and there was a pressure difference, then it would push and the volume would no longer be the same. Because the gas will have energy to do work in that case. Are you with me? Yes, it's free to move without friction. So if it's on equilibrium like that, then that's a stupid question, right? Then it becomes the same question as the other question with the two things holding. If it's like sitting like that in equilibrium, what's the pressure on both sides? I mean,
Because I thought that it was simple, but it actually has something else behind it.
all right, let's do more piston stuff. This time we're solving for temperature. So we rewrite the equation PV equals over NR and then temperature. They have the same amount of N, so N is out of the comparison. R is already out to begin with. All you have to worry about is P and V. Area is doubled on the top, which makes volume what? Weighted by a factor of what? 4. Increasing volume by a factor of 4.
No, wait, they're the same volume. The area increases, so the pressure increases.
No, they don't.
Decreases.
This does not have the same volume as that, guys.
It's not the same height. Oh no.
They have the same height of thing, but you're doubling the area, so this is more volume than that one does, by a factor of 2. Now you have to know about the pressure.
Factor of 4.
But then
That pressure has to be, no it's not, yeah. You can tell that this one has more pressure. By a factor of 2 also, but then there's a factor of 4 with the area, since, right?
There's no factor of 4 in the area.
Yes, there is. Oh, you're not doubling the radius, you're doubling the area already. Thank you guys. So it becomes, yeah, go get it. So it becomes what? 4 times the picture? Yes? All right. You get, it's 4 times. Okay.
But is it, because since the weight is twice as well, does it stay the same?
No, it's increased the pressure. No, it's both on top. Top, twice more pressure, twice more volume. So it becomes 4 times the temperature.
Oh, yeah.
Always solve the equation for what you're looking for. Yes. This one has twice the volume and twice the pressure, so 4 times the temperature. A would be less than the B, right? Because it has half the area and half the pressure.
well, yeah, it's small. The greater.
Now remember the pressure thing. You can get the pressure from the weight, because the third law thing. Whatever pressure this has is matching the 4 newtons there. But the oh, see, this is why we have people like that think in the class. Oh, you guys are good. I make mistakes too. She didn't see it. Get that later.
It's the same.
No, it's not. It's going to change the pressure now. Because pressure.
I just did the math about that.
Good. Get Legos as well. 8.
One is 19.6 and one is 19.62.
No. We'll talk about it's force per area
Yeah.
is pressure.
The area, so
Yeah, so if you do
So you increase the force by a factor of 2, but increase the area by a factor of 2, so pressure is the same. And then the only thing that matters then is the fact that the volume won't be the same. Volume will be the same.
That's what I told
So
you.
then it's 2 times, not 4 times the temperature. It's still less.
So B would be great.
At the beginning, we were like 2 times, and then go 4.
No, it is less than, but not because it's 4 times less. It's 2 times less.
So wait, pressure? What happens to pressure?
Pressure is force over unit area. There is twice as much force in this side, but there's also twice as much area. So the pressure is the same for both. However, the volume of this guy is twice as bigger, so it's twice the temperature. All right? Okay. All right. Ooh. What is, somebody look it up if you don't have it with you right now. If you have a book, you can help out. There's a formula for internal energy of an ideal monatomic gas. And I thought it was 1/2 of like, so, yeah, I figured that out. One is 3/2 and the other one is 2/2 of something. I need to find out formula, please. Sorry that I'm not prepared. These are very important though. It's the whole argumentation thing. So let's see if we can figure this one out. I'm working on something. It's not relevant for this. I'm just trying to remember because it's something we didn't talk about yet. And I want to make sure we do. Also, one thing that we did talk about, where does the potential energy that a gas have come from? The kinetic energy is the movement of the molecules. What's the potential? So when you're talking about the total internal energy of a gas, right? You can talk about how much the molecules are moving, and also the potential. What is that potential? Why would a gas have more potential than the other? Internal energy of a gas. Yeah. What is it?
It's U equals 3 over 2 NKT.
Yes. NKT? Right. And then there's a one that's 5/2, which I don't know when it applies. But an ideal monatomic glass, which is basically none gas that you ever work with, except you're talking about like helium or, right? What the hell's a monatomic gas? Like all the noble gases, that's it. Anything else is diatomic, right? Oxygen, nitrogen, hydrogen, right? They're all diatomic. But either way, this is it internal energy or potential energy that it says? Right. That's potential energy. Are you with me? On top of that, it can also have kinetic energy, and that's the movement that it's doing. Are you with me? What does that depend on, though? The internal energy of a gas. The number of molecules that it has, right? And the temperature of it as well. Huh? Yeah. This is the number of molecules.
Molecules or moles?
I think it's...
Because molecules is over...
it's little n.
So it's moles.
Most. Big N is molecules.
And then to find the mole, you do the big N over Avogadro?
Yes. I don't think they're going to make you do that too much. But, okay. Hey, have you been looking at this while we've been sitting here, or are you just letting it sit in the board? Come on. Must I always read so you do it? Come on.
I'm confused.
You're going to pull the pin, and then the piston can move.
But since it's isolated, heat won't escape, but there's pressure.
So there's no heat loss, right?
But you can't gain heat either.
Right.
It doesn't come out like...
Exactly.
Of course.
But the pressure increases or decreases.
Once the pin is out, the pressure on the gas,
It either goes up or down.
no, there'll be pressure on the gas for sure.
Yeah, but he says it doesn't know if it goes up. If it goes up, the pressure...
So on top, the piston is 8 kilometers out of this. The student who is asked what will happen to the temperature of the gas after the piston is unlocked. Now, think about it. PV equals nRT, right? So this is it changing the number of molecules that's in there? Is it changing the constants in there? No, of course not. Is it trying to change the volume?
Yeah. It's decreasing it.
And it goes down So pressure increases, but the volume decreases.
All right, the volume decreases and pressure increases. So what is that? What kind of thermal process is that?
Adiabatic. No, isothermal.
Where P and V both move at the same time. We did this the first day, right? If it's like this, it's isobaric, iron the curve. Let's review that. This is important. Okay? All right. So if it's moving like that, that's isobaric. What's work?
The work is an area.
Which is what? P times V. Right? And then things we have to look at is Q. Things we have to look at is delta T. Right?
No U.
You have to look at what happens to pressure. Right? So that you can look at delta P and we can look at delta V. Let's do that for every single one of them. Review this, have this written down in your mind so you can do it. So if we're doing something like that, by definition, delta V is 0. Something always is 0. Right? Now, the volume is changing up in this process. Okay? So it's increasing, right? And then, by the way, you could travel backwards. So it doesn't have to be increased. But the volume is changing. So if the volume is increasing, let's think about the rest, right? So you'll be doing positive work or negative work? Positive work, right? You're doing work, right? Because the volume is increasing, right? And it would be P times V, right? Now, what's the formula for Q? There's a pressure for that.
MC delta T.
Now, like this.
Oh. Internal plus.
No, sorry, U
Is
work
Is work plus.
No, that's not right. Delta U equals W
Plus Q.
plus Q. Right? Now, so let's think about this thing. Q minus W equals delta U. All right, of course, because because it's 0 if these are the same, right? It makes sense. So if you do enough work to take all the heat away from the gas, then there's no change or so forth. Okay, so anyways, so if I do work on this, but the internal energy of the heat, there's no heat exchange, right? What happens to the internal energy of the system?
Oh, it stays the same.
No heat exchange, no heat access to the system, right? But I do work, right? So it's a positive, and I do work on it, right? So what happens to
Internal energy.
that's negative work? So it'll be positive. It will be. Now you have to make sure it makes sense to you. The internal energy of the system is supposed to go up if you're doing work on something, right? If the gas is doing work, that's the thing. This W represents the work that's done by the gas. Work done on the gas is negative of that. Write that down somewhere. W is work done by the gas. If you do it on the gas,
So the gas
it becomes negative.
If the gas pushes something, it's negative work.
If the gas is doing work,
Positive.
so by the gas, then he lost some of his internal energy because he had to do work with that,
But it'd be positive work.
right?
The
Yes,
gas does positive work.
right. The gas does positive work. Therefore, it must have lost some internal energy goes down, right? Unless heat was added to it, it can do work, right, without heat. Are you with me? So if you gain heat, it doesn't have to give up its own internal energy to do that. Do you understand what I'm trying to say? This is the heat exchanged. The heat's the change. But if it's an insulated system and the gas is doing work, it must have lost internal energy. Does that make sense? Now, this is interesting. Now, if you do work on the gas, this becomes negative and internal energy goes up. Right? Okay. Now, let's think about this then. So if the gas is doing work over here, what's happening to Q? So solve for Q. It will be what? Delta U plus W, right? So if this is happening, what would happen if U is staying? It depends on what happens to U, delta U, right? But if you don't change the internal thing, then it would cause heat would have to be increased, right? Or if they have to have heat released. How does this typically do to temperature? Let's think about the temperature of this. B staying the same and volume is increasing. What probably will do the temperature here? In this scenario, temperature would have to go up. All right. So then let's talk about isothermic process. Remember how? So isochoric process. That's when it's like this, right? Because volume does not change, but there's no work. No change in volume, no work, because there's no area under the curve, right? What happens to the pressure? The pressure changes, right? Either up or down. Okay. So if you change the if you're doing no work though, then Q is the internal temperature of the thing, and then what about the temperature? Pressure still increasing, so the temperature is still going up. All right, unless you lower the volume, lower the pressure, in which case the temperature goes down. Right. Now, if you're increasing the pressure, depends what you do. If you increase the pressure, then you're gonna raise the temperature. If you decrease the pressure, you're gonna lower the temperature. Okay. Isothermic looks like this, right? Because you're changing both the pressure and the temperature. No, sorry, and the volume, right? Now, going back to our process here, we're changing both the temperature and the volume. Does it have to be isothermic to be like that? No, it could be isobaric, right? It doesn't have to be isothermic. It could be isobaric where the line is, the slope is different, right? Oh, adiabatic, sorry, that's something. Adiabatic. Now, the piston will not move.
What would be the derivative of the isothermal? Nothing?
Huh?
You know how the integration of the isothermal is?
I don't think there's a meaning for that you're looking for. All right? The piston will move, but we don't know which way. Whether it moves up or down, though, since the cylinder is insulated, the temperature of the gas cannot change during the process. Now, this is the thing. You're changing pressure and volume.
Good afternoon, teachers and students. Please pardon for interruption. Please release all junior varsity and varsity girls volleyball.
Okay, so let's do it again. You're losing. I read clear that the pressure on the gas will increase. The pressure will increase, right? But that the volume, the piston will move, but we don't know which way. If you say the volume will decrease, then you're saying that he's wrong, because the piston would move. Or else will the volume increase, right? The pin is there holding that weight, right? And the gas is also holding that weight, not necessarily, because the pin is there. But the gas is exerting a certain pressure, right? When I pull that pin out, the gas will have to exert more pressure to hold that piston up, right? And it will be compressed into a point where it's going to have to do that. Doesn't that seem natural to everybody, right? That the gas will have to be compressed here? If the gas wouldn't have been compressed, it would have been pushing this thing up the whole time around. All right? No, it would. So in other words, the question that we have to know, and that's a very important question, is this gas trying to push this thing up right now? Is the pin holding the thing from not falling, or holding the gas from not pushing this up? That's what we don't know. What do you mean? You don't know that. If you take the pin out, maybe the gas has enough pressure to do what? To push the weight up. If the gas is hot enough, right? If the gas, so let's remember the pressure. What's the pressure? And so if the gas is hot enough, right, or whatever, and it has enough internal energy, it will have energy to. It might be exerting pressure here. I'll give you a personal example of this. When you pop a balloon, what happens to the gas? Expands immediately, pushing on that balloon, right? Now the balloon, as you're holding it here, how does the pressure inside compare to the atmospheric pressure? Think about it. Don't say something stupid. It's the same. If it wasn't the same, it would be squeezed. If it was greater, it would be expanding. Right? Now, as I start rising up with that balloon, say in an airplane, what's going to happen to this? It will start expanding because the outside loses pressure. If instead of go to the bottom of the ocean, what happens to the balloon? It will compress, right? But as long as I'm holding it like here, what will happen to it? It will maintain that shape, which means the pressures are equalized. Are you with me there? Now, we don't know that that's the case here. We don't know that that's like equalized. If we take the spin out, this may just be exerting pressure that will pull this thing up. We don't know that.
Exactly, but if the pin is there, it's holding it on.
We don't know that. The pin could be preventing the gas to pushing it up.
But how could a pin prevent it?
Because it's holding the plate in place.
Oh, it could.
Yeah.
Oh, okay.
So, the student is asked what will happen to the temperature of the gas after the piston is unlocked. Now, the piston will not move. Well, the piston will move. We don't know which way.
So we do both?
Does that make sense? What he's saying? We don't know.
Wait,
Because
does it have to move? Can't it just stay there? It's possible.
It could be all of these.
Yeah, it could already be.
you're right as well. Give him Legos because he caught me wrong. It's like 3 Legos. So, he's right. The piston may or may not move. What do we need to find out for that?
The force exerting, the
I just
force
did-
exerting is the same as the weight.
What?
The force of the gas is the
Yes, if the pressure of the gas equals the pressure of the weight, the pin will not move. Nothing will change. Everything will be the same the way that it is. If the gas has less pressure, then the pressure that's being now exerted on it as the pin takes out, the gas will then compress. What will happen to the temperature? Volume is decreasing too.
Oh yeah, just yeah.
So it could be isothermic or it could be isobaric. No, sorry, what do you call? Adiabatic. If it's adiabatic, the temperature will not stay the same, right? But if it's isothermic, it will stay the same. So even then we don't know what's going to happen to the temperature. Are you with me? Now, what about if it goes up? The temperature will be decreasing. Because at that point we're increasing the volume and there's no way to decrease the volume and make the temperature stay the same. Alright, are you with me? And we'll have to do it. Is everybody clear on that? Now we have to correct the student. Whether it moves up or down though, since the cylinder is insulated, the temperature of the gas cannot change during the process. Think about what he's saying. Heat cannot escape.
Wait, from only that cylinder at the top. That's why I'm confused.
No, the whole thing is a cylinder.
It says like, I didn't say it's in your
You see what I'm saying? This is a system from which heat cannot escape. That's it. The heat, remember, Q, internal energy of the gas equals work plus Q, or minus Q. Q minus W, right? If I add heat, then this can be positive to make up for it. What does it mean when it's positive? Done by the gas, right? So that means the gas can do work, right? So if instead, yes, I don't have to lose heat, but the heat could go to work, which the gas can do to expand. So expanding counts as getting that heat. Are you with me? So the temperature could change though because of that. This is actually a very important point. Yes. Yes, if it expands, you cool down because you are losing the temperature, not because the heat goes missing. And that's actually a very important thing because heat is not a thing that goes. It's not even a thing that is. It's a thing that passes. Remember that? So the gas doesn't have heat. So you can't think of it as, this is where it becomes a problem. You can think of this, because this is insulated, it can't lose heat. That doesn't make sense because it doesn't have heat to lose. Heat is something that's passed. Are you with me? So what could happen though, it can lose thermal energy. To what? To the work that was done to make it, does that make sense? So that doesn't make sense. We could lower the temperature regardless of what moved up and down. So the question then is that we do not know what's going to happen. We have not enough information to know what's going to happen. It depends on the pressure of the gas. We do not know, right? But we do know that whether it moves, and you know the second part doesn't make sense though. So you can criticize the second part of the student argument. Are you with me? Based on his lack of understanding about the fact that the thermal energy can be converted to work. that could make the gas expand, lowering the temperature. Right? That's what I was looking for there. On the other hand, we do not know if it's going to stay the same, move up or move down. That depends on the pressure of the gas. Right? And even if it moves down, we do not know if it's the temperature will stay the same, because it could be isothermic or adiabatic. Right? We don't know. Yes. Again, if it's compressing the gas, right? Pressure is changing. That means something did work on the gas instead of the gas doing work. Hold on. If something did work on the gas by the equation, that's what? A negative number being put in here, right? But if the internal energy cannot stay the same, that means that the heat will be produced. Well, we'll have to change the temperature. Yes, it could.
Does this thing have answers?
But it's not about that. It's about arguing the answers.
I know.
Oh, like the key? No, that's not been released. I actually think that the people that wrote this are the same people that write the AP test too, so that they don't actually want the answers released. All right, let's see if you learned something. By the way, today's the last day. Next 4 days will be spent with labs. Okay, on this. Today is Tuesday? Wednesday? Okay. What? I know. We don't need to do it today though. If we do a game, it's going to be combined. And I said if. And the reason why I'm saying if is because you are getting points for doing this, and this is conceptual practice. So I'd rather do another lab day than do more conceptual practice. You see what I'm saying?
So guarantee 4 topics.
So we will have enough time to do a bunch of labs is what I want. Okay?
Each lab day is what?
Huh? 20 points, always. If we have a full day.
So we should get around 80.
That's right.
And then on level
50. So you can almost get 2 levels there. And then these things are points too. So in the last 3 classes, you should have been able to get a bunch of points.
How are the points of these?
Every question that you answer is 1.
Towards the last
But it says 30 points right there. Almost. But we also did ranking tasks on the other class.
For mastery, we should have like 100.
Answer, people. Answer it. Remember what we thought about? How do we know the pressure of the gas by looking at the diagrams? By the weight. It must be matching it, right? The pistons are at rest, even though they're free to move. So you start thinking of PV equals nRT and all that blah, blah, blah. Does that matter? No, it does not matter. Does the area of it, all this thing matters? No, it doesn't matter. They're asking for the pressure of the gases. Oh, you're right, because they now have the same size. So the pressure on them is different. What I meant is that, do you need to know the volume of the grass and stuff like that? Not really. This matters for another reason, because you need to know that to figure out the pressure. How do we do problems like this? We compare B to A, right? So, do they have different masses here? No, so the force is the same, but the area is going to be what? No, this is diameter this time. So 4 times. Okay, so this got 4 times the area with the same force, so a quarter of the pressure, right? Quarter of A. By the same token, same area, but 2 times the force, 2 times the pressure, this will be 2 times A. Very good. And then the other one is just same as A. So we rank them C, D, A, and then B. Right? You have to explain why this is 1/4. You guys understand why it's a quarter? Yeah. Okay. So, oh, I get it. These are options that you can use for each option, for each question. Are you with me? So, the change that they're describing, we'll do one of these things and then you explain why, right? So, the new system has a lighter piston, which is this part right there, but the same metal disc is floating on top of it. So, we know that this gas has enough pressure to hold that thing up, right? But if you take it out and put a lighter disc on it, what does that mean?
The force is less because it's lighter.
It will decrease the pressure of the system,
So two.
right? Two, but what's your reasoning? The gas will have to push up less, right, to hold that weight. Mm-hmm.
Okay, but it wouldn't stay up and have
If you're talking about the same gas, yes. If you magically switch them immediately, right? So if you were to magically remove those 2 newtons somehow, like IFB, the gas would have enough internal energy to do work and expand. That's what he's asking. But that's not what the question is asking. You know what I'm saying? You just say if you had that and you just change that to thing, you represent it, that's like the ranking test, almost. But now, he made a good point. If it was possible to make the mass of this instantaneously become half its mass, what would happen?
Wouldn't it drop slightly?
No, the gas had that much pressure, right? And then it would have internal energy to do work and make this thing expand, right? Yes. 2 separate things, yes. All right. On the next one, the new system has a heavier metal disc for the same piston. Same token, more pressure, right? Are you with me? C.
Good afternoon, Matter Lake.
A lighter piston and a lighter disc.
Do you want to travel
Decrease the pressure.
cruise to the Greek islands? How about
All right.
to the
A
ancient
smaller cross-section area in the
Vatican
piston
Museum of
also,
Rome? Then join us for
but the
our
weight of the piston is the same, and the disc is also the same. So now we're making the pressure smaller because the
Students interested in true details.
pressure higher.
Visit Mr. Brew in room
Because you have making it
413, in room 414,
more force,
Ms.
more.
Garcia in room 134, or Ms. Mandano in room 223. See you October 13th for our spring break trip meeting.
I'm gonna make sure I do these. Hold on a second.
Join the Italian Club for our first meeting ever. It will be on October 7th at 245 in room 514. Be a VIP, very Italian person. Keep calm, it's
Hey!
a neon party on October
Keep
9th
paying
from
attention.
7 to 11.
How does the work of this gas compare to the work done by that process?
Only.
Why? How do you know?
The high school cafeteria.
Same area under the curve. Now remember, when you're moving left, you subtract the area from the work done. Are you with me? So when I moved right, I did all that work. The 3 columns. But when I moved left, I am now compressing the gas, so work was done on it. So I lost that work. Are you with me? So that means the net is to be 1 box. But this is, I did 2 took 1. This is what I did 3 took 2. So either way is the same, right? Don't rate, so these is fine. Which box does my work? That line or that line? Top line or bottom line? You would have to count the boxes to figure that out for sure. Right? 1, 2, 3, 4, 5, 6, so forth. It looks as if the top might win it by just a little bit, I think. But you have to count the boxes. You know what to do, right? What type of process is it present? Is it isothermic? No, because if it was isothermic, well, how would it look like? Which means, no, it wouldn't be straight, it would be that. If you see that, don't assume it's isothermic though unless they tell you, because it could be adiabatic, right? This is going to be changing temperature, right? Now let's think about how it will be changed temperature. If listen, I am making the pressure go down by how much here? 2, while the volume is going by a factor of 6, 5. So pressure's going down 2, while this is going up 5. So it's going to go up. Does that make sense? So temperature will go up. Do you understand what that means? Yes, the slope. The slope is what temperature will do. Kind of. No, don't think of it that way. Alright, look at the adiabatic versus isothermal. You see? Hey, this is important. Pay attention. Which one does more work?
One direction.
Isothermal or adiabatic? Isothermal does more work. Make sure you know that. Okay? Which one does no work? Quickly. A. Which one does the most work? Okay. Which one is most likely isobaric? Oh, it says it.
Bear Bowl will take place tomorrow at 12:30 at Lakes on the Green Park. Entrance is free and food and beverages will be sold. And remember that tomorrow is an early release day. High school will be dismissed at 11:45 and middle school will be dismissed at 12:30. Please go to the Bear Bowl at Lakes on the Green Park. We hope to see you all there.
All right. Temperature. Temperature changes. Right? Temperature changes. Does this one change temperature? Let's think about it. Isobaric ones always do. Temperature should be going what? Up because volume is going up by a factor of 2. Right? Well, that's 1. Yeah, you're right. No, you're doubling. So it's by a factor of 2. Right? In this case, you're doubling the volume, but as you double the volume, you're also decreasing the pressure a little bit, so it won't be going up as much. Are you with me? On this case, it's going to go down by you're going to half it while it doubles. So what happens to the temperature? And the term isothermal is about the same thing. Right? So you see why the isothermal is isothermal? Because it takes a path like that. Similar to the linear one. That's why that's trying to teach you. Guys, stay with me 5 minutes. Seriously. We need the time. I forgot these graphs. But we did these already. Let me see this really quick. Anything else in here? Oh, the only other thing is efficiency. Don't worry about that. That's it. All right, let's do one question in efficiency. That's it. Listen up. So, no, this is not in the curriculum. We don't have to worry about it. Not like that. Now we kind of know energy cycles.
So we don't need to know about
as far as I know. All right, guys. If I'm right, there's 4 days left. Check the calendar. If there's 4 days left, there's 4 days of labs. Okay? Huh? Unless I change my mind and take the last day and do a conceptual game for both topics. Now turn it in. Alright, turn it in. Next class I get it back. Huh? You're doing it, right?
Yeah, I know. Just letting you know that I chose you as a teacher.
Oh, okay.